There are 10 elements: scandium, titanium, so raster board, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Out of this, the oxygen state +2 shown by manganese, iron, cobalt, nickel, copper, zinc. And +1 oxygen state also shown by the copper, especially. Okay. Now, scandium shows +3. It is titanium also +4. Vanadium along with +3, +5. Chromium +3, +4, +5, +6. Manganese +3, +4, +5, +6, +7. Already in the last class I discussed, there is 1 unit difference in the oxygen states. When compared with the S and P block, it is different. In P block, the difference between the two oxygen state is minimum 2. That is, for example, oxygen group +2, +4, +6. Sulfur can able to give the 3 oxygen state +2, +4, +6. But here manganese give the +2, +3, +4, +5, +6, +7. 1 unit difference. +4, +5, +6. Cobalt up to +5. Nickel up to +3, +4. Copper shows only +1, +2. Zinc shows +2 only. Now, out of these oxygen states, the first elements that is up to scandium to chromium, +3 is more stable oxygen state. Later, +2 is more stable than +3, followed by remaining all +2, +2 is more stable. Listen to me. First half of the elements +3 stability, next half of the element +2 stability, but this is reversed. Even though it is first 1, 2, 3, 4, 5, these 4 element +3, it is +2. The last 4 element +2, this is +3. Rather than the expectation, it is different between these two. Whatever I given in the brackets, this bracket is more stable with the common compound, more stable oxidation state with common compounds, chlorides, halides, sulfides, etc. And secondly, I am writing in the square brackets like this, +3, here +2, and here +1. That is, these 3 oxygen states are medium stable in the normal compounds. For example, copper, in case of copper, CuI, cuprous iodide, Cu2I2 or otherwise, +1 state. And in case of manganese, MnO2, it is a medium stable, sorry, this is not, this is medium stable, +4 is a medium stable, not +3, sorry. MnO2 here, +4 is the common oxygen state for this. +2 and +4 more stable here. Here +2 and +3 more stable. And here +1 and +2 more stable. But most important, all higher oxygen states are stable with only with the oxygen and fluorine. With oxygen and fluorine. For example, KMnO4 manganate, permanganate, plus 7. Chromium trioxide, RCr2O3. Cr2O3, here plus 6 is more oxidation state, more stable oxidation state. More stable oxidation state. Manganese oxide plus 4. Cuprous iodide plus 1. These are the, but copper iodide, Cu(I2) is the more stable compound plus 2. It is less stable compound. So there are three types of oxidation states are there, stable oxidation states. Even though they are having the variable oxidation states, 1, 2, 3 types of oxidation states. Plus 3 and plus 5 plus 6 are unstable. Plus 2, plus 4, plus 7 are stable. Plus 7 is, for example, in case of manganese, plus 7 is stable with the oxygen and fluoride compounds. Plus 2 is stable with the normal compounds, that is manganese sulfate, manganese chloride, manganese bromide, etc. This is MnO4 is also somewhat stable, but this is more stable, is less stable, such as compounds of manganese oxide, manganese dioxide, MnO2. So in higher oxidation states such as plus 5, plus 6, plus 7, etc. can be shown, can be exhibited only in those compound oxides or fluorides. Without oxygen fluorine, these oxidation states cannot be exhibited. And the plesioid is the highest oxidation state in the plesioid. I am writing here, plesioid is the highest oxidation state shown by the osmium and iridium. In the seventh group, in the manganese, iron, ruthenium, osmium, and ruthenium and osmium belongs to iron group. Iron, ruthenium, osmium. Ruthenium and osmium shows the +8 oxidation state also, but iron shows only +6, even though it is having the 8 electrons in the valency shell. Here 3d6, 4s2, 8 electrons are there, but 8 electrons cannot be lost, cannot lose. But in the osmium, ruthenium, with oxygen, all 8 electrons can be can lose and form the +8 oxidation state. Because of the high electronegativity and small size, iron is exhibit only +6, not +8. Even though there is possibility to show the +8 except that is the electrons of 8 electrons, but it cannot lose 8 electrons. But in case of ruthenium osmium, they can lose 8 electrons with oxygen and fluorine because they are large in size, the electronegativity less, and they lose easily the electrons. So before going to in detail to explain the detail, I am going to discuss one most important point here. Why manganese plus, out of manganese plus 2 and manganese plus 4, both three are, these two are stable oxidation states. Manganese plus 3 is highly unstable. Highly unstable. Highly unstable. These are two stable states. Hence, manganese plus 3 undergo double decomposition. Plus 3. Manganese plus 3 oxidation state, it is 3d4, 4s0. It is the electron configuration of manganese plus 4. All of you know very well manganese is 3d5, 4s2. After losing 3 electrons, after 3 electron losing, with Mn plus 3, it is the oxidation state of manganese plus 3. It is 3d4. 3d4 means in the d orbitals, 4 electrons are there. 4 electrons. It is unstable. All of you know very well. It is either 3G, ETG, T2G. Either 3D3 is more stable. 3D3 is more stable. 3D3 is more stable. Or 3D5 is more stable. 3D3 is more stable. 3D5 is more stable. It is e.g. it is T2G in octahedral environment. Either this is stable, either this is stable, but 3D4 is unstable because this is 1, 2, 3, 4 unstable configuration. To get the stable configuration, this can gain the one electron or lose the one electron. By gaining and losing the one electron, the stable convert into stable. If it lose the electron to this, we will get the 3D3. If gain the one electron, it is called 3D5. It is 3D3, it is 3D5. It is 3D4. Hence, it undergo Mn plus 3 converted. It is called reduction. By reducing the Mn plus 3, we will get the Mn plus 2. By oxidizing the Mn plus 3, we are getting Mn plus 4. But which is more stable out of these two means Mn plus 2 is more stable. Hence, Mn plus 3 acting as a mostly reducing agent rather than the oxidizing agent. So Mn plus 3 compounds, whenever if you are having, they undergo oxidation as well as reduction based on their nature of the compounds. So similarly, Mn plus 5, Mn plus 7, it undergo oxidation to give the reduction to give the Mn plus 4, Mn plus 2 in acidic media and basic media. So it is second point we will discuss later. So what I am going to explain here, listen to me carefully. It is undergo double decomposition. So to give that Mn plus 3 compounds wherever if you find, immediately they convert into Mn plus 4 or Mn plus 2 depending upon situation. Mostly they can convert into Mn plus 2 to get the stability. And the second most important is out of the Mn plus 2, Fe plus 3. These both are stable. Both are highly stable. Fe plus 3, both are highly stable. Why both are highly stable? Because it is having 3D5, 4H0. It is also having 3D5, 4H0. But Fe plus 2 and Mn plus 3 are unstable. These are unstable. Why? It is having the 3D6, 4S0. It is having the 3D4, 5S0. See here, most important, 3D4, 5S0. So after losing 3 electron, we are getting unstable configuration, hence it is unstable. After gaining 1 electron, we are getting unstable configuration, 3D6. But somewhat stable, but not it is not stabilized 3D5. Hence, Fe plus 2 always convert into Fe plus 3 on exposure to air. Fe plus 2 always convert to Fe plus 3 on exposing to air. So sorry. Fe plus 2 always convert to Fe plus 3 on exposing to air. It is oxidation. Hence, Fe plus 3 is 3D, 5, 4S0, stable. 3D6, 4S0. On losing electron, Fe plus 2 compounds convert into Fe plus 3 compounds. That's why ferrous sulfate is, if you are stored in a container, in a beaker, after several days, it converts into ferric sulfate. Ferrous convert into ferric. Fe plus 2 into Fe plus 3. This is due to 3D6 is unstable configuration. On long exposure to the oxygen environment, due to the reaction of oxygen, slowly undergo oxidation to give the Fe plus 3. But similarly, Mn plus 3 slowly convert into Mn plus 2 by taking 1 electron. That means here Fe plus 2 compounds are undergo oxidation, that is they act as reducing nature. Mn plus 3 undergo reduction, that is it act as a oxidizing nature. That is, whenever electrons are gaining, it is called oxidation. Electron is losing, called reduction. So this is difference between these two. So why Fe plus 2 is more, Fe plus 3 is more stable than the Fe plus 2? Why Mn plus 2 is more stable than the Mn plus 3? We have explained. That is, this is due to electronic configuration, stable electron configuration. The stability of Mn plus 2 and Fe plus 3 will be there. Hence, we have justified that plus 3, first line plus 3, and here plus 2, followed by the plus 3. It is stability of the scandium, titanium, vanadium, chromium, manganese, iron. The first series having the more stable plus 3 because size is large. Left hand side, size is large, easily lose the electrons. Hence plus 3, total electrons, more electrons, along with the s electrons, d electrons also lost. But right side, starting from iron and chromium up to zinc, they have small size, more electronegativity compared with this. Hence, they are not losing 3 electrons. That is only s orbitals will lose electrons, but not the d orbitals, because the nucleus of those atoms strongly hold the d orbitals. Hence, plus 3 and plus 2. But here it is reversed. Here it is reversed because why it is reversed means because of electron configuration. The stability of oxygen states not only depends upon the electron configuration, not only depends on size and electronegativity, also depends upon the electron configuration. The stable electron configuration of manganese plus 2 and Fe plus 3 is due to half-filled electron configuration. This was not seen in the Mn plus 3 and Fe plus 2, even though their size difference has manganese is also having the more size, but because of electron configuration, Mn plus 2 is stable. Iron, almost one more point, manganese and iron almost same size. So now we will discuss now oxygen state is over. Any doubt is there, you can type here, I can answer. Otherwise, I am unmuting. Any doubts in case of oxygen states? Now, coming to the atomic radius. Sorry. Atomic radius. So, the atomic radius means, listen to me, atomic radius or size of the atoms, D block compounds. So, I'm making unmute you. I can answer, but unnecessarily don't discuss. Yeah, you can self unmute and ask the questions, anyone, and after that immediately close it. Okay. So I am going to discuss now atomic radius followed by the electronic configuration. Sorry. Anyone? Hello. Yeah. So now next point. I discussed oxygen state in the last class. Now I'm going to discuss atomic radius. So anyone can answer what happens to the atomic radius in a period? In a period.
It decreases across the period.
Yeah. Repeat.
Decreases with increasing atomic radius.
Only one. Anjali, you can write. You can say that what happens to the atomic radius in a period. Decrease along the period. Next. About what of the group?
Atomic number is more the atomic.
Okay. So I am going to ask one question. Out of the zirconium and hafnium, which has a larger size? Anyone can say, otherwise type. Hafnium. Okay. Any other one? Any other answers? Yeah. All of you saying hafnium. Okay, very good. Malesh, zirconium. Okay. Next. Okay. Okay. So all are you saying that titanium, zirconium, hafnium is a big group? According to your knowledge, all of you saying hafnium is larger size. Few are saying zirconium is larger size. But what I am saying, zirconium, hafnium are equal size, almost equal size. It is atomic radius on the y-axis. Here atoms, titanium, zirconium, hafnium. Titanium size is smaller. As moving to the down to the group, zirconium is more, followed by the size almost same. Listen to me. Zirconium and hafnium almost same size. First number one. So according to your knowledge, hafnium is more size. Majority answers. Keep in mind. Not only zirconium, hafnium, each and every 4D and 5D, 4D and 5D series elements are almost equal size. Yeah, almost equal size. Okay. So what I am telling here, the size of the fourth period and fifth period, that is called zirconium, hafnium, niobium, tantalum, followed by vanadium, chromium, molybdenum, tungsten, technetium, rhenium. What is that? Ruthenium, osmium. All these are having up to cadmium, mercury. These sizes are almost same. All these sizes are same. This is due to lanthanide contraction. Keep in the mind lanthanide contraction. That is scandium, yttrium, lanthanum, actinium. Here it is 21, 39, it is 40, it is 72. But here it is not 72. It is not 71. It is 57. 57 to 72. What are there in between that? Lanthanides are there. 14 elements lanthanides are there. Similarly, 57 plus 32, it is 89. After that, we are going to get the hafnium, rutherfordium 104. 104 rutherfordium. I think I'm not correct. You can correct one. 104. 89. In between that, again 14 elements are there called actinides. Listen to me, because F block also I'm going to explain. So these are the lanthanides. Because of the lanthanides are joining between the 57 and 72, 14 elements are coming in between the lanthanide and hafnium. In that lanthanides, the differentiating electron enters in the n-2 f orbital, that is 4f orbital here, 5f orbital here. The 4f and 5f orbitals are having the very much large size, diffused size, the large size. In that accommodated 14 electrons cannot have the more density. They do not attract, do not prevent the, prevent the nuclear force to go and act on the valence electrons. Hence, size of the atoms rapidly decreases. This phenomenon is called as lanthanide contraction. Because of the lanthanide contraction, after lanthanum, whatever the element hafnium having the reducing in the size, and almost its size equal to the element above the it. That is zirconium. Tantalum, neodymium, same size. You should keep in the mind. Because of this, most of the important properties such as, because all of you know very well, the electronegativity, electron affinity, and ionization potential, electropositivity of the all these depends upon the nuclear force and size of the atom. Here, size of the atom indirectly depends upon the Lambda contraction. These are all these sizes are same. Hence, the below elements, hafnium is having the more electronegativity than the zirconium. Hafnium has the less electropositivity than the zirconium. Hafnium has the highest density. Density also very high for this. So I'm going to explain one by one. So keep in the mind, the size of the fourth period element, fourth D block, fourth D series, and fifth D series are almost same. The reason is lanthanide contraction. So because of lanthanide contraction, what happens? I'm going to explain now, one by one. But before going to that, you have to know the first of all atomic radius of all these, because these are very important. In the coordination compound, the stability of the complex compound depends completely on these only. I am not teaching D block here. I am teaching you coordination compounds mainly. So here, listen to me. Palladium CN6 -4, palladium +2. Platinum CN6 -4, platinum +2. Compound 1, compound 2. You can type or say that which is more stable compound. Which is more stable compound? What is the difference here? -4, -4. Complex and charge is same. Ligand, same ligand. Ligand atmosphere same. Oxygen state same. Only palladium and platinum, the elements are different. Oh yes, size is different. Now tell me, which is more stable according to your knowledge? Which is more stable? Either 1 or 2. Yeah. Pranati, give an answer. 2. Very good. Any other answers? If you are you saying that this compound is stable? Why? Because platinum has 1. Who is that? Avanti. Beta Avanti. It is not correct. Your answer is not correct. 1 is not correct, Nana. Prashant. So I am going to explain. See there here. So palladium and platinum size is same. It is palladium size. It is platinum size. Why the sizes are same? You know the answer very well. Lanthanide contraction. Yes or not? Now, what is the oxygen state? Same. Size is same. Charge is same. The ionic potential size, charge to size is same. All of you know very well. About the stability of the oxygen states, coordination compounds, stability of the complex compounds, factors affecting the stability of the complex compounds. In that, stability explained by the first of all size of the metal, oxygen state of the metal. If size and oxygen state is same, then it is depends upon the electronegativity of the element. I am repeating the stability of the complex compounds. The stability of the complex compound depends upon the nature of the ligand, nature of the metal, chelation, etc. I'm coming to the nature of the metal. Nature of the metal means here 3 points are there. One is size of the charge and electronegativity. When size and charge same, electronegativity gives the main role. Tell me that now. What is the answer? What is the answer? Which is stable out of these two now? Now tell me answer. 2 or 1? Irfana and Avanti. Now Avanti, you got it now, answer. Because why? Because electron weight of platinum is greater because it is having the only palladium 46 protons. Here having the 76 protons. Here how much it is? 28, 46. Here 78 protons. See here, same size, same charge. But the attraction force is more for this platinum because 32 protons are extra. Hence, here the stability is beyond our expectation. Hence, you have to know the atomic radius or size of the de Broglie elements effectively to learn better the coordination compound chemistry. Hence, I discussed this because to create the interest while learning the atomic radius. Because most of the times inorganic chemistry get boring. Without boring, we want to teach means you have to apply this to the all topics. Now, what is the importance of the de Broglie elements? Why we have to read the de Broglie elements effectively? To learn the coordinate complexes, coordination chemistry very easily and with effectively. And de Broglie answers also can be easily expressed in the examination. Total inorganic chemistry will become very easy. Now, I am going to ask you, out of copper and zinc, which has large size? Answer. చెప్పచ్చు నోటితో చెప్పచ్చు లేదా టైప్ చేయొచ్చు. Copper, zinc. Yeah. Which has large size? Copper. Zinc. Iron. Copper. Very good. Copper. Yeah. So most of you are telling copper. One, iron. You can on the mic and explain. Tell me that why. Your Prashant, you can answer. Avantika. Okay. So 2 members, Aruna and Prashant. Iddaru they said that zinc. Why? Under copper చెప్తే ఇద్దరు జింక్ చెప్పారు. ఒకసారి చెప్పండి అమ్మా ఆన్సర్. దిక్కు అన్మ్యూట్ అవ్వండి, చెప్పండి. Both. Which is more size? Both cannot have the more size. అన్మ్యూట్ చేశాను నేను ఆల్రెడీ. చెప్పండి, ఎవరు చెప్తారు? So majority I am getting answer copper is more size. Who said that zinc is more size? They have to answer me whether electrons increasing. Okay, yeah. So what happens? Nana, Aruna and Parthi, either Jeppandi, either zinc or copper again. Repeat it, your answer. Don't waste the time. So here, copper size is less than the zinc. Both are 4D series. Okay. Both are in a period. Actually, copper should be more size, zinc should be small size. But here, that is not there. Both are 3D series, no problem. In the 3D series, copper should have the more size according to your knowledge. Zinc should have the less size. It is your correct according to your knowledge. But what happens is actually copper has less size than the zinc. It is not due to the exceptional configuration. I am going to explain you that is in detail now why copper has less size than the zinc. Yeah. Which shielding effect you? Okay. So I'm coming to the point now. So what is, I'm going to write the size here. Then anyone can go and check the book. Why? And tomorrow you have to come with the doubts, number of doubts. So listen to me. It is see here. It is scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Out of vanadium, almost vanadium and zinc is almost same size. The atomic radius. First scandium size is more, followed by titanium, followed by the vanadium, zinc almost same, followed by the copper, followed by the chromium, followed by the manganese. Almost these are same. Almost the size of iron, cobalt, nickel, copper, nickel are same, almost same. Keep in the mind this curve. Starting decreases like this and remains constant and increases. According to your knowledge, from left to right, what should happen? Atomic radius must decrease. Decreasing, decreasing, decreasing. From manganese to nickel, almost size is constant. After nickel, in the copper, nickel to copper, size increased rather than decreased. Copper to zinc again increased. After zinc again decreased. After zinc as usually decreased. But from manganese to zinc, what happens? Manganese to zinc, what happens? Size decreases, remains constant, increases. Tell me that which is the least size of the D block element? Which is the least size of the D block element? Nickel. Nickel is the smallest size in the 3D series. Which is large size? Scandium, titanium, vanadium. Scandium, titanium, vanadium, chromium, large size. So which are comparable? Zinc and vanadium almost comparable in size. So manganese and iron almost equal. Manganese and iron almost equal. Keep in the mind, like zirconium and hafnium. How the zirconium hafnium are equal in size, almost. Similarly, manganese and iron also almost equal. Followed by there is small decrease in the iron to cobalt to nickel, iron to cobalt, cobalt to nickel, followed by size increases. Keep in the mind. Keep in the mind. So why, how, etc. I will explain after the completion of the topic. So I am writing here. కొంచెం బోర్డు పెద్ద చేస్తాను పట్టదు కొంచెం చూసుకోండి గ్రాఫ్ గీసుకోండి మంచిగా ఫస్ట్ సిరీస్ స్టార్టింగ్ ఫ్రమ్ పొటాషియం calcium, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Next series, same size again increase because group. Copper from after potassium, what is that? Rubidium, calcium, strontium, yttrium, zirconium, niobium, chromium తర్వాత ఏమొస్తారా molybdenum, here technetium, ruthenium, rhodium, palladium, silver, cadmium. Write down this, most important. Next, rubidium, cesium, barium, lanthanum. Now it is most important. So after lanthanum, what happens? We will get the hafnium, and niobium, tantalum, lanthanum, same. Mercury, aurum, platinum, iridium, osmium, molybdenum, తర్వాత tungsten, niobium, tantalum. So ఒక్కసారి I am enlarging. See, I think this is because of this rapid decrease because of lanthanide contraction. But ఒక్క నిమిషం, ఇంతకన్నా క్లియర్గా కష్టం. చూడండి, ఇది పొటాషియం, కాల్షియం, స్కాండియం, టిటానియం, వనాడియం, క్రోమియం, మ్యాంగనీస్, ఐరన్, కోబాల్ట్, నికెల్, కాపర్, జింక్. దీని మీద ఇంకొక లైన్, సైజ్ ఇంక్రీజ్ అవుతుంది. జూమ్ అయింది, 100% జూమ్ చేశాను నాన్న. ఇప్పుడు చూడండి, ఎనీ ప్రాబ్లం, ఎనీ ఓకేనా? నా ఓకే, రైట్. Because potassium, starting from here, potassium, starting from here, potassium, calcium, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. The inmate size increase అవుతుంది because group rubidium, strontium, yttrium, zirconium, niobium, same. But after that, what happens? Cesium, in case of cesium, listen to me, కొంచెం తగ్గిస్తాను. In case of cesium, rubidium, potassium, rubidium, cesium size increase. Cesium to beryllium decrease, cesium to barium decrease, barium to lanthanum decrease. After lanthanum, we are getting hafnium. Zirconium, hafnium, same size. Niobium, tantalum, same size. Molybdenum, tungsten, same size. Technetium, radium, same size. Ruthenium, same size. Almost same size. ఇది మీకు ఈ గ్రాఫ్ మైండ్ లో పెట్టుకుంటే you can answer the easily the which is more size, which is less size in the examination. So tell me that what is the least size of the D block elements? Nickel. What is the large size of the D block elements? Lanthanum and mercury. Why zinc and vanadium almost equal size? Zinc and vanadium equal size. Zinc here, vanadium here, almost equal size. Actually, left to right, what should happen? Size should be decreased. According to our knowledge of intermediate and previous knowledge, left to right period, nucleus protons increase, outside electrons increase, size decrease. Slowly from left to right, size decrease. But it is true, but in some cases, the factors affecting the size of the atoms not only depends upon the nuclear force and distance between the nucleus and valence electrons. It depends upon other than these two, shielding effect, and one more is inter-electron repulsions. Okay, this is most important. Inter-electron repulsions are most important to explain the size of the atoms. So I am repeating, the size of the atoms depends upon the number one, nuclear force, that is number of protons present in the nucleus. Number two, distance from the nucleus and valence electrons. Number three, shielding effect. Number four, that is most important, inter-electron repulsions. So that inter-electron repulsions will create this type of environment. Up to here, no inter-electron repulsions because 3D1, 3D2, 3D3, 3D4, 3D5 means, listen to me, 5 atoms, 1, 3D1, 3D2, 3D3, 3D4, 3D5, up to manganese 3D5. Whenever iron comes, one electron join here. The joining electron will create inter-electron repulsions because repulsion size of the atom increases. Size of the atom increases even though here 25 protons, 26 protons. One proton increased, one electron increased. But size is same. Actually, when proton increases, what happens? Electronegativity should increase and catch hold tightly. Iron size should be decreased. But here, whatever the electron joined in the d orbital undergo repulsion. Because of repulsion, they enlarge. Because of enlarge, electron cloud move away from the nucleus. Hence, size increases. Hence, these two become same size. So I will explain in detail about this. Keep in the mind first of all this. What happened here? 1, 2, 3, 4. Here, electrons are pairing, slowly pairing. Here, electron cloud increasing. Because electron cloud increase, what happens? They are repelling. Because repelling, what happens? They are moving away from the nucleus. What nucleus is trying? One proton increase, one proton increase. Attraction increases. One electron increasing, not normal increase. It is not normal increase. What happens here? They are pairing. They are pairing. Because of pairing, what happens? Inter-electrons undergo repulsions. Because repulsion, what happens? They enlarge and away from the nucleus, size increases rather than decrease. Hence, we are getting almost the same size. Anyone, if you are not having clarity, you can pose the doubt. I can explain in detail. I will explain in detail if you are having any problem to understand this. So overall, what happens here? The size of the all these are same. Whenever 3D10 becomes, the inter-electron repulsions are dominating on the nucleus attraction. Inter-electron repulsions are more dominating than the nuclear force increased. Year to year increase in nuclear force is less and inter-electron repulsions are more, and they are moving away from the nucleus, and the nickel to copper size increases rather than decrease. Copper to zinc also increase. After zinc, D block is completely filled. The electrons enter the p orbital and again attraction increases. They are going to decrease size and size and size. Finally, in the bromine, after bromine, in the krypton, again size increases because of same inter-electron repulsion. And keep in the mind, always zero group elements are having the larger size than the first group element. Neon has more size than the lithium. Keep in the mind. Potassium, argon, krypton. Krypton has more size than the potassium. Argon has more size than the sodium. But left to right, what should happen? Left to right, what should happen? Size should decrease. Sodium to magnesium, magnesium to aluminium, aluminium to what is that? Silicon, phosphorus, sulfur, chlorine. Size decreases and decreases and decreases. Suddenly, in the argon size increases. That's why I'm going to explain that also now, because to understand this, once listen to me that what is the size effect of the lithium to? It is lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. It is neon. Which is more size? Neon is more size, followed by the lithium, beryllium, boron, carbon, nitrogen, oxygen, Fluorine. Fluorine is the least size one. Neon is the large size one. Next part lithium. ఎవరైనా ఏమనుకుంటారు, సార్ మాకు చిన్నప్పటి నుంచి సార్ చెప్పింది ఏంటంటే ఎడమ నుంచి కుడికి, లెఫ్ట్ టు రైట్ సైజ్ డిక్రీజెస్. హెన్స్ లిథియం is large size, neon is small size. But it is not correct. Up to fluorine size decreases. From fluorine to neon size increases. Anyone can say why? Why fluorine to neon size decreases? Here, fluorine 9 protons, 9 electrons. Neon has 10 protons, electrons. Which should have the less size according to your knowledge? Tell me. Yeah. Tell me, which should have the more size? Neon. Why neon should be more size? Even though 10 protons are 10 electrons attracting, here only 9 electrons attracting. Which is attracting more? Which has more attraction power? Fluorine. Then which should have the why fluorine? Fluorine has only 9 electrons. Neon has 10 electrons. Which is more having the 10 protons? 9 protons. Tell me which is more attracting power? Why? Why fluorine? Fluorine has a 9, is a 10, which is more magnetic power. Forget your knowledge. What I am asking, number of protons is more, attraction power is more or not? Okay, small size, okay, but I am not telling you. How can you know the small size it is? Without my why explanation, you don't know it is having large size. నేను మీకు ఎక్స్ప్లెయిన్ చేయకపోతే మీరు ఫ్లోరిన్ కన్నా నియాన్ చిన్నది అనుకునే వాళ్ళు కావచ్చు. మరి why oxygen is more size than the fluorine? Why oxygen has more size than the fluorine? 10 10 9 9. Here 8 8. Why not oxygen less size than the fluorine? Electronegativity depends on the only number of protons. Number of protons are more, electronegativity more. Van der Waals forces. Okay, Teju. So here you are not having the clarity. First, listen to me. Attraction depends upon the nucleus. Nucleus having the positive protons, positive charge protons. Protons are going to attract the electrons. If number of protons are more, it should have the more attraction power. But when the size is large, attraction power decreases. But from lithium to fluorine, size decreases. But suddenly, why in the neon size increases? You have to catch my point. Why in the neon size increases suddenly? Because here up to fluorine, listen to me, up to fluorine, only 3p5 is there, 2p5 is there, 2s to 2p5. Whenever if you come to neon, electron joins here. See here, 6 electrons join in the 3 orbitals. Repulsion between the electrons increases. Yes, again. Because of electron repulsion, the attraction power 9 to 10, 1 proton increase, but 1 electron increase. Because of electron increase, more repulsion increase than the more attraction. Attraction was dominated by the repulsion. That's why size increase. That's why size increase. And one more important point I'm going to explain. I'm going to write here 2 graphs. Which graph is correct one? You can explain to me. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, Cl. Oxygen, fluorine, neon. Lithium, beryllium, boron, carbon, nitrogen. Here, lithium, fluorine, neon, beryllium, boron, carbon, nitrogen, oxygen. Which is correct graph? 1, 2. See here, I am writing here. Oxygen, fluorine almost same size. Here, fluorine, oxygen, nitrogen, carbon. What is the difference between these two? In case of one was regular decrease, same decrease. Finally, because of increase. Here, more decrease, most decrease, more decrease, small decrease, very less, very less, very less, very less, very less. Yes, very good. So it is correct one. So what happens here? Nitrogen to oxygen. Now up to nitrogen, what happens? 3. Now oxygen to nitrogen to oxygen, what happens? 4. Inter-electron repulsion started. Inter-electron repulsion started. Hence, what happens? Size do not decrease more. Size do not decrease more. In oxygen, next fluorine. Size almost nitrogen, oxygen, fluorine almost same size. Small decrease. That's all. If the inter-electron repulsion was not there, we will get like this. Then after that, complete electrons are repelled. Suddenly, the domination of the inter-electron repulsion increases, size rapidly increases, and equal to neon, lithium. But up to here, fluorine is very, very small size. In the questions may ask, difference between the lithium, beryllium large, carbon, nitrogen is very small, oxygen, fluorine is very, very small difference in the size. This is because shielding effect and as well as inter-electron repulsions of the electron cloud. Similarly, in case what we discussed just before our D block elements, in D block element also, what happened? Because of the same inter-electron repulsions, we are getting like this. Here, up to here 3D5. Up to here, no inter-electron repulsions. Listen to me carefully, it is most important in the future. Now, in case of 3D6, inter-electron repulsion started. Next, 3D7, 2 pairs, 3D8, 4 pairs. In copper, 5 pairs, 310. Hence, copper has more inter-electron repulsions. Manganese do not have inter-electron repulsions. But immediately after manganese to copper, manganese to iron, one proton increase, one electron increase. Increase one proton attracts, increase one electron because of pairing repulse. Both are balanced. Hence, iron and manganese almost same. This size, small size almost same. In copper, suddenly inter-electron repulsion increase like neon, and zinc is having the more size, followed by the size decreases. So keep in the mind now, if you know the atomic radius, if the know atomic radius properly, remaining all properties will be discussed easily. All of you know very well, electronegativity depends upon the size of the atom. Electropositivity depends on size of the atom. Electron affinity depends upon the size of the atom, and electron configuration. Density depends upon the size. So all periodic properties of the elements completely depends upon the atomic radius and electron configuration. Hence, one must know the atomic radius and electron configuration of the total periodic table. It is very effective to answer anything in the future. Not only in inorganic chemistry, it is very much useful in the organic chemistry and physical chemistry also. So I'm going to give the importance of this one. I'm going to explain one more important point. So boron, aluminium, gallium, indium, thallium. Boron, aluminium, indium, gallium, indium, thallium. Anyone can say that which is more size? Boron, aluminium, gallium, indium, thallium. So which is the largest size? Answer. So all of in a very small boron. Yeah, thallium. Next, gallium. Very good. Next. After thallium. So according to your now, after first thallium, next indium, next gallium, next aluminium, next boron. According to your knowledge, yes or not? Top to the bottom, size increase. Okay, no problem. But you are going to wonder that what are the sizes? Listen to me. Boron to aluminium size decrease rapidly. After aluminium to gallium, small little bit increase. Small increase. Indium to thallium decrease and small decrease. Small thing. That is boron is 0.8, 1.23, 1.24, 1.55, 1.5, 1.55 angstroms. It is the size of the boron, aluminium, gallium, indium, thallium. You can write down and keep in the mind. Aluminium, gallium, indium, thallium. So it is size. It is atomic number. So see here, what happens here? Aluminium, gallium, our size are different. Sorry. Almost same size. Sorry, I'm sorry here. Almost same size. 1.23. Almost same size, somewhat gallium is more. Okay, sorry. So size increases. Listen to me. What I written? Sorry, I'm writing wrongly. Inversely, I would write. It is a correct order. Boron 0.8 angstroms, 1.22, 1.23, 1.22, 1.5, 1.55. Difference is 0.05. Here difference is 0.01. Here difference is 0.242. Here difference is 0.23. So overall, which is more size? Thallium, followed by indium, followed by aluminium, almost equivalent small size by gallium, followed by boron. Now answer anyone. Why aluminium has more size or almost equal size than gallium, even though it is third period, it is fourth period. I am explaining D block only, but not only D block is most important, it is also most important. Evarana cheppandamma. Aluminium and gallium almost equal size. Gallium has small size less than aluminium rather than more size. Top to the bottom size should increase. Boron small size, aluminium large, then gallium should large and going on increasing. But what happened here? Boron to aluminium rapid increase, more increase. Aluminium to gallium, no increase. somewhat small decrease and increase. Everywhere increase there, but year to year large increase, it is very, very minute increase, small increase. All of you know very well this is because lanthanide contraction effect. All of you know very well already, just before I explained zirconium hafnium, niobium tantalum, technetium rhenium, ruthenium osmium, rm gold, rm silver, as well as cadmium mercury. Just the after that we are having the indium thallium. After that we are having the tin lead. Like that, all these are having the up to bismuth. Above bismuth, what is there? Antimony bismuth. Up to antimony bismuth, this small size difference is there. Like this is because of the lanthanide contraction. It is the effect of post lanthanide contraction. మీకు ఎబ్లాక్ చెప్తారు. What is lanthanide contraction and what's its effect on the post lanthanide elements? Lanthanide element తర్వాత వచ్చే వాటి మీద ఈ ప్రభావం ఎలా ఉంటుందో చెప్పమంటే మనం చెప్పొచ్చు. ఇవన్నీ ఇప్పుడు చెప్పినవన్నీ all atomic radius of the 4D and 5D almost equal because of the lanthanide contraction. Whenever atomic radius is same, then what happens? All the properties, remaining clear properties are reversed rather than our expectation. Hence, the chemistry of the developed elements are different rather than we expect. Similarly, here also same, but why it is decreased? All y is same. If it is same, y is same, why it decreased? Anyone answer? Anyone answer? After zinc, we will get the gallium. After zinc, we will get the helium. After lanthanum, we will get the hafnium. Lanthanum, hafnium. After lanthanum, 14 lanthanum elements. After lanthanum, 14 lanthanum elements. Lanthanide contraction, hafnium becomes zirconium, same size. Similarly, in the deep black elements, because of the different shielding effect of the variable shielding effect of the d orbitals up to scandium to manganese, very, very less shielding effect, and manganese to nickel comparatively more shielding effect due to interactive repulsions, and nickel to zinc strong shielding effect and opposing the nucleus and size increasing. Due to all these problems, size of the gallium decreased because of shielding effect of the d orbitals. If d orbitals behave like f orbitals, gallium size must be very, very less than the aluminum. If d orbitals behave like f orbitals, contraction is more going on. Aluminium, gallium size very small than the aluminium. If d orbitals behave like s and p orbitals, the gallium size should be more than the aluminium. That's why boron to aluminium, why size increased? Because shielding effect is more because by s and p orbitals. Boron to aluminium size increase because one new shell appears, and otherwise S and P black elements are having the high shielding effect. But aluminium to gallium, no, one orbit is changed, but d orbitals having the less shielding effect. Hence, size of the gallium decreased and equal to the aluminium, smaller less than the aluminium. If d orbitals behave like f orbitals, that is minimum no shielding effect, the gallium size could have very, 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 very small, and half of this. That is, we can expect like this now. Then we can expect like this, almost equal to boron. In between the boron and aluminium, it should be there, but probably d orbitals having the shielding effect more than the f orbitals, less than the p orbital, due to before upfilling very less shielding effect, after upfilling more shielding effect. It is average between the p and the d orbitals. Hence, the size effect will be different like that. Hence, we can justify our answer. The graph is like slowly decreases and without change and again increase. because of inter-electron diffusion. This behavior will affect on the gallium size. Hence, gallium will be equal to above aluminum, and gallium is safe. Then, because of that, aluminum has more less electronegativity, and it has the more electronegativity because electronegativity depends upon the size of the atoms. So thallium is the highest electronegativity, followed by the indium, followed by the gallium, followed by the boron. Aluminum is the least electronegative effect. Electronegativity is more for the smaller size one, boron. After boron, thallium. After thallium, only remaining will come. So aluminum is the least electronegative element in the periodic table in this group because its size is very high. Its size is very high. So because of this, first boron, very small size, more electronegative. After boron, what happens? Electronegativity fall down because size increases rapidly. So keep in mind, always electronegativity depends upon the size of the atoms, compared to size of the atoms. Out of aluminum, gallium, which is more electronegative, compulsory gallium is the more electronegative because it has 18 protons extra. Aluminum, in case of aluminum, what happens? 13 protons, but gallium has 31 protons. Same size. Size same, but 31 protons, gallium has the same size. 18 protons, aluminum have the same size. Then which is the more electronegativity? Automatically gallium. Like zirconium, hafnium, niobium, tantalum, mercury, cadmium, etc. Like these are also most important. So keep in mind, electronegativity, electropositivity, ionization potentials, as well as density, electronity, all these depends upon the only size of the atoms and electron configuration. So if you know the properties of elements effectively, their chemical reactivity, their stability of the atomic compound, etc., one should know the atomic periodic table, their sizes effectively. Hence, and I'm sure that you are going to learn very, very important factors of matters in the next class. Within the detail time. Ionization potential 10 minutes, electronegativity 5 minutes, and all other properties within half an hour. I will complete the total properties and I will enter the oxygen, other factors, catalytic effects, etc. Within half an hour, our chapter will be actively whatever is given here. So now any doubt you can raise now. After that, I will go further. Anyone? Anyone? Tell me the importance of periodic table, importance of periodic properties, most important in all chemical reactions. So you must learn it. Why the size are more or less? Tell me that which is more size now? Out of scandium, titanium, vanadium. Okay, I can give one order. Anyone can answer. Choose the correct one following. A, B, C, D. Which is correct? Size. Zinc, copper, nickel, vanadium. Vanadium, zinc, vanadium, copper, nickel. D. Very good. So if you are not within the class, what you may answer? If you are not listened to my, if you are not sent to my class, what you may answer? Suppose, see, very good. That's all. Keep in mind, from tomorrow onward, our topic must be effective if you come with a observation study on this. ఎట్లా ఉంటుందంటే, for example, you are going to answer, not myself. What is electronegativity? So you know the sizes, you can answer immediately. Any difference is there, I will explain. One or two. Ionization potential. So tell me that now, what is the, you can answer now with your own. So IP values. Which is correct? Which is correct here? 2. Copper zinc. Copper has more electronegativity. Ionization potential. Zinc. No. How can you say? Just before C is Y. Zinc is small size, right side. If you are without from left to right, what happens? Size decreases. Vanadium in left side, zinc right side. Vanadium, copper, nickel, copper, zinc. According to the periodic table, left to right. But our explanation gives vanadium is more, followed by almost zinc, vanadium almost zinc is more, vanadium less. Next followed by the copper, but nickel. Nickel is small size. Now in this case, what happens? Ionization potential. Okay, I will give the worry somewhat easy. So tell me that zirconium, hafnium, 1. Zirconium, hafnium, 2. Which is the correct answer? IP, ionization potential. According to your knowledge. Yeah. 2. 1. Anand Sagar, 1. Okay. 2. 2. చెప్పండి, మీ ఇష్టం వచ్చి చెప్పండి, నో ప్రాబ్లం, చదవని చెప్పండి. 2 2 2. యా 2 2 2. Anand Sagar, you have not followed. So here zirconium, hafnium. Actually, titanium, top of the periodic table, zirconium, hafnium. Size increase like this. As per size, Sairam, listen to me. Titanium is a small size, more electronegative. If the size of the hafnium is very high, it should be less electronegative. But what happens here? These two have the same size. Just before I given. But even though they are same size, it has only 40 protons. It has 72 protons. Same size, but it has the 32 protons are extra, attracting more the electrons. Hence, it has the more electronegative. Hence, answer is this one. Second is the answer. Why they are same size? Why they are same size? Oh, listen to me. One person, that means it is 32. It is like the same size, but the magnetic power is 30 times greater than this one. Then its magnetic power is more. So like that, it is going to attract more the electrons. Okay, followed. Like that, you can answer tomorrow. Everyone, you can ready, prepare, and any doubts are there before the class, only you have to ask. Then I will complete all these topics within 1 hour, 1.5 hour. Topic will be completed. Total deep lab will be completed. But you have to learn this. Rebecca 1.5 hour total topic will be covered, and I will go to the F lab. But you have to go through this most effectively. Left to right, what happens? Top to bottom, what happens? Why size is same? Why size is more? Why size is less? Why? What is the reasons? All reasons you have to keep in the mind. It is very easy. It is very easy. It is very easy to answer in the examination. So any doubts you can ask now. Before going to conclude the class, if you have any doubts, you can ask. I am making unmute you. Yeah, you can answer now. అందరు క్లోజ్ చేయండి అమ్మా, అవసరం ఉన్న వాళ్ళు ఓపెన్ చేయండి. యా, ఎనీ డౌట్స్? వెల్కమ్. సో
Sir, vanadium. Sir,
yeah, vanadium. Once go through the any book or the sizes. Answer. Question please. Question please. Zinc and vanadium almost equal sizes according to. It's just small size difference may be there, but actually zinc should be very less in the D block elements, and it is more than the chromium, more than the manganese, iron, etc., copper, nickel. Why? Because of interelectron equation I discussed. If you have any doubts, you can ask me. If you are not having doubts or clarifications, I can close the topic. Shall I close? Fifth to sixth period is same size, not all. 5D series and 4D series are same size. 4D series and 5D at the fifth and sixth group, not all. Only in the D block, that too from titanium, zirconium to zinc, cadmium, mercury. Not in the case of scandium, yttrium, lanthanum, actinium. Lanthanum and actinium size increase as usually. Starts from zirconium, hafnium, because after lanthanum, actinium, we are getting lanthanides and actinides. We will get the actinide contraction as well as lanthanide contraction. Because of that, from third B group, that is called the fourth B group, that is called fourth B, means titanium, zirconium, hafnium. After that, Rutherford 4D, I think so, 104. In this case, here to here zirconium, it is lanthanide contraction. Here to here, it is actinide contraction. Both are both contractions. From here to from copper, that is called zinc, cadmium, mercury, that group, up to that group, followed by the indium, thallium, followed by the carbon, tin, lead, antimony, bismuth. Up to that, this will work out. It is called factors affecting the lanthanide contraction on the post lanthanide elements. Lanthanide element tarvata vache D block మూలకాల పైన, P block మూలకాల పైన, ముఖ్యంగా 4D 5D పైన. ఆ తర్వాత అప్ టు అదేంటి బోరాన్ గ్రూప్, కార్బన్ గ్రూప్ అండ్ నైట్రోజన్ గ్రూప్. అంతే, మళ్ళీ ఆక్సిజన్ గ్రూప్ లో రాదు, ఎందుకంటే అక్కడ మళ్ళీ ఇంటరాక్టివ్ రిలేషన్స్ వస్తాయి. 4P4 వస్తుంది అక్కడ, 5P4 5P6 వచ్చిన తర్వాత మళ్ళీ అక్కడ కెమిస్ట్రీ మారిపోతుంది, సైజెస్ పెరుగుతాయి. సో అదొక చిన్న డిఫరెంట్ అది. అందుకని మనకు ఈ అప్ టు జస్ట్ ఆల్మోస్ట్ ఎండింగ్ దాకా కూడా ఈ ఎఫెక్ట్ ఉంటుంది, కానీ మొత్తం జింక్, క్యాడ్మియం, మెర్క్యూరీ వరకు ఎఫెక్ట్ వరకు ఉంటుంది, టిన్, లెడ్ వాటి వరకు ఉంటుంది ఈ సైజ్ ఎఫెక్ట్, లాంథనైడ్ కాంట్రాస్ట్ ఎఫెక్ట్. సో బికాస్ ఆఫ్ దిస్ ప్రాపర్టీస్ ఆర్ డిఫరెంట్. ఇవి మారినాయంటే ఆటోమేటిక్గా అయనేషన్ పొటెన్షియల్, ఎలక్ట్రాన్ అఫినిటీ, డెన్సిటీస్ అన్ని మారుతాయి. అవి ఎట్లా మారుతాయనే విషయాన్ని చూసుకుందాం. ఫస్ట్ డెన్సిటీ కొంచెం చూసుకుందాం. డెన్సిటీ అంటే ఏంటమ్మా? మాస్ బై వాల్యూమ్, మాస్ ఆఫ్ ద ఆటమ్ బై ఇట్స్ వాల్యూమ్. లెఫ్ట్ టు రైట్ మెల్లగా ఏమవుతుంది? టాప్ టు బాటమ్ ఏమవుతుంది? జిర్కోనియం 40 ప్రోటాన్స్ 40 న్యూట్రాన్స్ ఫర్ ఎగ్జాంపుల్, 80. దాని కింద ఏముంది? హాఫ్నియం 72 ప్రోటాన్స్ 72 న్యూట్రాన్స్ అప్రాక్సిమేట్లీ 140. అంటే 80 ఎక్కడ, 140 ఎక్కడ? అంటే 60 పెరిగింది ఒకసారి, కానీ సైజ్ మాత్రం సేమ్. weight by volume. Weight is more, but volume is same. Then what happens? Density increases. Density is equal to mass by volume. Mass increasing 60, 180, 140, 60. But size same. Mass by size is not same. Density more. Density increases in a period and group also. Suddenly the density of the zirconium to hafnium suddenly density increases, almost become double. Similarly, ruthenium to osmium, palladium to platinum, suddenly density increases. At the same time, left to right, size decreases, and osmium and iridium is the largest density elements in the periodic table. After that, decreases. Nickel వరకు పెరుగుతుంది. కాపర్ జింక్ లో డెన్సిటీ తగ్గుతుంది. ఎంత తగ్గుతుంది? కాపర్ సైజ్ ఇంక్రీజ్, బట్ మాస్ ఇంక్రీజ్, సైజ్ ఇంక్రీజ్. అప్ టు నికెల్, మాస్ ఇంక్రీజ్, size decreases. Hence, nickel has the largest density in the D series, 3D. 3D లో నికెల్ కి లార్జ్ డెన్సిటీ ఉంటుంది. అలానే ఆల్మోస్ట్ ఏముంటాయి? ఐరన్, కోబాల్ట్, నికెల్ ఈ మూడు కలిపి ఆల్మోస్ట్ సేమ్ ఉంటాయి, బట్ డెన్సిటీ చాలా ఎక్కువ ఉంటుంది. డెన్సిటీ పెరుగుతూ వచ్చి మళ్ళీ తగ్గుతుంది. అంటే కాపర్ జింక్ లో డెన్సిటీ పెరగాల్సింది పోయి తగ్గుతుంది. Why? It is because of the size effect. Why size is like this? Because of the shielding effect and inter-electron repulsion. That's contraction. సో ఇవన్నిటికీ ఒక లింక్ ఉంటుంది. ఈ లింక్ గురించి మనం చెప్పుకోవాలంటే మనకు ఇది రావాలి. ఇది ఒకటే కాదు, చాలా ఉన్నాయి పాయింట్స్. ఈ సైజుని బట్టి మనం చాలా అంశాలు చెప్పుకోవచ్చు, చాలా ఈజీగా అర్థం చేయించుకోవచ్చు, ఈజీగా మనం ఎగ్జామినేషన్ లో రాసేయచ్చు. సో అందుకని మీరు వితౌట్ ఎనీ మీకు ఏ డౌట్ వస్తే ఆ డౌట్ అడిగేయండి. ఓకేనా? యా, కంటిన్యూ. ఓకే, ఎనీవన్? I think you don't have doubts and read today. చదవండి ఒకసారి. వాళ్ళ రేపు ఫస్ట్ 10 minutes లో డౌట్స్ అడగాలి. అర్థం కానున్నా చెక్ చేసుకున్నాక బుక్ లో మీకు ఏమైనా డిఫరెన్స్ కనిపించినా, ఏదైనా మ్యాటర్లో డిఫరెన్స్ కనిపించినా రేపు అడగాలి. రేపటి క్లాస్ క్రూషియల్. ఈ చదవకుండా వస్తే ఏం అర్థం కాదు. ఇప్పుడు చెప్పిందని చదువుకొని వస్తే కోఆర్డినేషన్ కాంపౌండ్స్ అయిపోయిన తర్వాత మీకు ఇబ్బంది లేకుండా ఉంటారు. కాపర్ జింక్ లో డెన్సిటీ ఆర్డర్. నికెల్ వరకు డెన్సిటీ పెరుగుతుందిరా, కాపర్ జింక్ లో తగ్గుతుంది. అప్ టు స్కాండియం టు నికెల్ density increases because size decreases, mass increases. Okay, I'm going to explain. Listen to me. రేపు ఎట్లా చెప్పేదే కానీ మళ్ళీ చెప్తున్నాను. చూడండి, స్కాండియం size is more, 21 plus 21 products and neutrons. Size small, 22 plus 22. So on. Manganese 25 plus 25. Iron 26 plus 26. Nickel 26 plus 26, 27 plus 27. Copper, cobalt, nickel 28 plus 28. Copper 29 plus 29, but size increased. Zinc 30 plus 30, size increased. చూడండి, ఇక్కడ ఏమవుతుంది? weight slowly increasing, density is equal to mass by volume. వాల్యూమ్ ఈజ్ డిక్రీజింగ్. కింద డినామినేటర్ తగ్గిపోతుంది, న్యూమరేటర్ పెరిగిపోతుంది. అప్పుడు ఏమవుతుంది? డెన్సిటీ షుడ్ ఇంక్రీజ్. ఇక్కడికి వచ్చిన తర్వాత నికెల్ హైయెస్ట్ డెన్సిటీ బికాస్ ఇట్ స్మాల్ సైజ్ అండ్ లార్జ్ మాస్. కింద తగ్గుతుంది, పైన పెరుగుతుంది. కింద తగ్గుతుంది, పైన ఏమవుతుంది? ఆటోమేటిక్ గా డెన్సిటీ పెరుగుతుంది. కానీ కాపర్ కచ్చారికి ఏమైంది? మాస్ పెరిగింది, వాల్యూమ్ కూడా పెరిగింది. ఎందుకు పెరిగింది వాల్యూమ్? ఇంటర్ ఎలక్ట్రాన్ రిపల్షన్. ఆఫ్టర్ దట్, because of the copper and zinc has the more size, the density is less than the remaining element. Keep in the mind. So ఇంకా మీకు చెప్పాలి, ప్లాటినం కన్నా ఐరన్ చాలా గట్టిగా ఉంటుంది, కాపర్ మెత్తగా ఉంటుంది, మెటాలిక్ నేచర్. ఇవన్నీ రేపు చెప్పుకుంటాము. ఓకే, I will explain later. Any doubt you can type now or ask. మళ్ళీ కిందికి వస్తే ఏమవుతుంది? సైజ్ పెరుగుతూ వచ్చి లేదర్ కాంట్రాక్షన్ వల్ల సడన్ గా సైజ్ సేమ్ ఉండిపోయి మాస్ ఎక్కువ అవుతుంది. కనుక కిందికి ఇక్కడ నుంచి ఇక్కడ వచ్చేసరికి డెన్సిటీ పెరుగుతుంది, కిందికి వచ్చేవరకు పెరుగుతుంది. కనుక ఈ మధ్యలో ఉన్న ఆస్మియం, ఇరిడియం ఇస్ ద లార్జెస్ట్ డెన్సిటీ ఎలిమెంట్స్ ఇన్ ద పీరియాడిక్ టేబుల్. osmium and iridium are the largest density elements in the periodic table. 22 grams per just ఇంత సైజ్ ఉన్నది. ఒక లిక్విడ్ డ్రాప్ అనేది 20 grams ఉంటుంది. 20 grams per cc అంటే ఎటు 1 సెంటీమీటర్ పొడవు 1 సెంటీమీటర్ ఎత్తు ఉన్నదాన్ని క్యూబిక్ సెంటీమీటర్ ఉన్నది అనుకోండి, దాని బరువు 22 grams ఉంటుంది. అంటే ఏంటన్నమాట, ఒక సెంటీమీటర్ పొడవు, సెంటీమీటర్ ఎత్తు, సెంటీమీటర్ చిన్న క్యూబ్ లాంటి దాన్ని తీసుకుంటే 22 గ్రాముల బరువు ఉంటుంది ఇరీడియం అండ్ ఆస్మియం. అదే అల్యూమినియం తీసుకుంటే 5 గ్రాములు 3 గ్రాములు ఉండదు. అంటే డెన్సిటీ ఎక్కువ ఉన్నప్పుడు బరువు ఎక్కువ ఉంటాయి, బాగా దగ్గరకు వస్తాయి. సో డెన్సిటీ ఎందుకు ఎక్కువ ఉంటుంది అంటే తక్కువ ఏరియాలో ఎక్కువ ఉంటాయి. దానికి కారణం ఏంటంటే సైజ్, మోర్ మాస్ ఆక్యుపై ద స్మాల్ సైజ్. దానికి కారణం ఏంటంటే లంథానిక్ ఇంటరాక్షన్ as well as b electrons interact or repulsion, both are going to support that one. Okay, any other one? Shall I close? Shall I close? Okay, so tomorrow be prepared, otherwise you will not be followed properly.
సార్ ఏం చేద్దామా?
చేద్దాం సార్.
ఓకే, థ్యాంక్ యూ సార్. రేపు మళ్ళీ ఆఫ్టర్నూన్ కంటిన్యూ